Okay, so let's get started because we have a full hour, I think, ahead of us.
Very good.
Very good. Hi, I'm Erin Stawinski. I'm a product and community manager for the Simon Initiative, and I'm here to welcome everyone to the Open Simon webinar series. For those who might be new, Open Simon is a learning engineering community working to improve learning outcomes for all. And this series is meant to provide instruction, examples, and demonstrations of learning engineering techniques and tools, and to just celebrate best practices in applied learning science. I apologize for any background noise. I'm here today at Microsoft headquarters to help with a presentation at the IMS Global Learning Analytics Summit. So I'm breaking off just for a few minutes to do this webinar, so I really appreciate you all being here. Today, and let me share my screen so we have something to look at here. Give me a second. So today we have with us Dr. Vasudeva Rao Aravind. And
yes, yeah, Vasudeva Rao Aravind, yeah, thank you.
Thank you. And he is an associate professor at Clarion University. Dr. Aravind was first introduced to CTAT-based tutors 3 years ago. And since then, he's designed, developed, and deployed tutors successfully in undergraduate classes in physics, computer science, and economics. And Dr. Aravind holds a PhD in materials science from Pennsylvania State University and currently teaches physics and physical sciences at Clarion University. And then we also have with us, to help later on, Dr. Vincent Alleviate, our own professor and director of undergraduate programs with the Computer Interaction Institute at CMU. So welcome everyone, and I'm going to turn it over to Dr. Aravind to give his presentation. And
thank you, Erin. Yeah, let me share my screen. All right, so I have made a small PowerPoint. I hope all of you can see the screen, yes?
Yes, we can see it.
Very good, very good. Oh, yeah, thank you, Erin, for the introduction. So yeah, let me just give a small overview of Clarion University. So my talk is titled Improving Student Learning with CTAT, a Practitioner's Perspective. That's what I hope to do. You know, I've been making tutors and using my tutors for the past 3 years at Clarion University. So I thought I'll share a little bit of my experience. So a little background about Clarion University before we start. So we are located about 80 miles north of Pittsburgh, not far from CMU. And we are one of the Pennsylvania state's 14 school system. The state of Pennsylvania, under its Pennsylvania State System of Higher Education, has 14 universities, and Clarion University is one of them. And we have about, Clarion University, we have about 6,000 students or so, including online students. So I have been teaching, and I teach physics, and as you might expect, we don't have a lot of physics majors. In fact, most of the students that we teach are not physics majors. Typically, we teach pre-medical students and students from all kinds of backgrounds, including history and arts and business. You know, everybody's required to take a course in physics. So we teach mostly physics as a service course, and we also have physics majors, about 20 or 30 of them. But most of the students we teach are non-physics majors. And also, a lot of our students come from in and around the Clarion area, which means, and Clarion, as you can see, is a very rural place in Pennsylvania. It's a rural place. So, and most of our students come from the rural high schools nearby surrounding Clarion. So, so this is what, so one of the problems that we often run into, just like me, I'm sure many people run into this problem all over the country. Physics is by nature a hard subject, which means that it needs a lot of practice to understand physics and internalize the concepts, and to be able to use these concepts in a real life situation, such as a problem solving situation. It takes a lot of practice. And many of the students that we teach here at Clarion University have not had a physics course throughout their high school. In fact, many of them come to college trying to learn physics for the very first time, never had a physics course in their classes, in their high schools. So it is a big challenge to be able to cover, and obviously just like other schools, we are also understaffed, one faculty. Typically we boast about small class sizes, a class size of about 25 or 30. That's typically the class size we have. But in spite of that, considering the amount of effort that it takes to make sure every student learns the subject to the maximum mastery, it is a big challenge. So what we would ideally like is, we would like the ideal situation would be a human tutor that can work with the students, ideally one tutor for every student. That would be the ideal case, who can provide practice in problem solving, and then provide detailed feedback to the teacher, and basically interact one-on-one with the student, providing complex interaction, trying to explain the physics of the problem, and making sure that the student understands problem solving to their best possible ability. Obviously, that is not possible because it takes a lot of effort and a lot of time, and that is not practical at all. So having a human tutor is impossible. Sometimes how people manage this situation is having students come over to talk to the professor during office hours. But even that has a limited ability because first of all, our office hours are limited, and it is not practical for every student to come and talk to the teacher during office hours. And in fact, a lot of students even hesitate to come and talk to the teacher to even see them in office hours. That's how it is. So what we wanted to do was we wanted to make a computer-based tutor that can provide practice in problem solving. It could be numerical problem solving. It could be conceptual problem solving. And such a tutor should be able to provide immediate feedback to the students, meaning the students should not have to wait for 1 week until their teacher grades their homework problems to know whether their answer is correct or incorrect. And the tutor should be able to provide an appropriate feedback with multiple hints at every step of the problem. And in addition to that, the tutor should be able to provide a detailed feedback to the teacher as to where the students are making mistakes, which could be due to some of the misconceptions that may have. So hopefully this teacher will be able to have a bird's eye view of whether there are any patterns in student errors, and whether these patterns are arising out of any misconceptions that students might have. And also, given the one-on-one nature, given the nature of the classroom, it needs to be completely authored by the teacher, because every class and every student, they have their own requirements, so the teacher would like to make the tutor unique to suit their teaching style and the learning style of their students. So, and sometimes there are some commercial tutors available, but the commercial tutors do not serve the purpose, because the teacher may want to make the tutor in a certain way, exactly catering to a particular need of the student population, but that is not possible from commercial tutors. So what we wanted was all required tools should be available free of cost, so that the teachers can make their own tutors. And of course, we are physics teachers, we are not computer programmers. So we should be able to author the tutors with no programming knowledge or little programming knowledge needed. And CTAT, the cognitive tutor authoring tools provided by Carnegie Mellon, it suits all these needs exactly very well. And we also have a great support from the CTAT team, because of which in the first place, we were able to make some tutors. So what I plan to do today is I will discuss some of the tutors that we made. First, I'll show some screenshots. I'll explain the tutor that we made, and then maybe I'll do a small demo of the tutor on the Tutor Shop website, so that we can sort of see it working live. So the first tutor that I want to talk about is a vector components tutor. So this is actually a very, very common phenomena in all physics related subjects. So we have the vector components tutor. So suppose I have a vector along the XY coordinate system in any random direction in the two-dimensional plane. The student should be able to split a vector along to its X and Y components. So in this tutor that we made, this consisted of about 20 to 25 problems, in which all the 25 problems, the pattern is the same, except that the direction of the arrow was different. In one case, it was lying in the first quadrant. Sometimes the arrow was in the second quadrant, and so on. So this is what the student has to do. The student has to look at the graph that is provided to them and then enter the value of the x component given by ax here. And then they have to enter the value of the y component here, ay here. And of course, if the student has, suppose the student does not know how to handle the problem, or maybe the student thinks that they know how to do the problem, but they made a careless error. In such scenarios, we should be able to provide feedback. So that's how we made the tutor. So as you can see here, first of all, when the student enters the value of ax, as soon as they enter the value, sometimes the value will be shown in, if the value is correct, if the answer is correct, then the answer will highlight in green, which means that the student's answer is correct, and then they can proceed to the next step. But if not, then the answer will highlight itself in red, which means that the student had made a mistake, and then they can try again. And if the students are stuck for some reason, for example, maybe a student feels, hey, I have no idea how to do this problem. Can somebody help me? Or maybe the student feels, hey, I know exactly how to do this problem, and this is how it should be done. So, and this is the answer I have, but I don't understand why the software is telling me it is wrong. So in such scenarios, we have this hint button that is made for the students so that they can ask for hints. So actually the hints are actually tiered in 3 different levels. So the first hint would be a soft hint, which will sort of just intended to push the students in the correct direction. The second hint is a little bit more direct, although it doesn't give the answer as such. And the third hint, we don't want to keep the students here forever, just getting stuck on this one problem. So the third hint is a hard hint, which basically tells the student what the answer is, right? So that hopefully they will learn from the answer, and then they can do the next problem correctly for themselves. So that's how we structured this tutor. Also CTAT allows us to do some learning analytics at the end of to look at the learning curves so that we can see how well the students are learning from the tutor. So this is what we did. So we implemented this with a class of about 30 students or so in my classroom in undergraduate physics. So they played with this tutor, they learned from this tutor. And at the end of the exercise, we tried to measure the learning curves. And while measuring the learning curves, initially, we assumed that doing the X and Y components correct is one single skill. So we used a single knowledge component model. And we find that the learning curve looks haphazard. It's choppy, it's not regular. So obviously, so something is wrong, in terms of splitting the splitting the exercise into knowledge components. So what we did was we went ahead and we made the assumption. Actually, this was done during one of our Learn Labs summer schools at Carnegie Mellon. So what we did was we assumed that when the finding the X and Y components correctly, when the components are positive as a single skill, and when the components are negative as another skill. For example, from my teaching experience, it's easy to make an assumption that when the vector lies along the first coordinate, the first quadrant, it's easier to do it, whereas when it occurs in the second or third or fourth quadrants, it's relatively harder. So that's the assumption that we started out with. So and then we saw that it is indeed true. So what we did was we split instead of using a single knowledge component model, we split this into 2 knowledge components, wherein we said that if so there are 2 possibilities, the X and Y components could be positive or negative. And then with this assumption, we saw that the learning curve were actually relatively smoother. So you see that the students are initially making a lot of errors, and then as they get more and more opportunities, as they try out the problems more and more, their error level falls practically to 0 as we go along. And also, this happens both for the positive component and also for the negative component. And one other thing that we see here is that when it comes to positive component, the students seem to make lesser number of errors, which tells us that probably it's easier to find the X and Y components when the components are positive, whereas when the components are negative, it's a little bit harder. So which is basically shown here. The error level is higher when it comes to negative components. And also we see another thing, we see that when we try to fit this to, let's say, an exponential decay curve, we also see that within 5 or 10 tries, the students seem to be getting the point. The students seem to be getting a fairly good idea within 5 to 10 trials. And the fact that we did about 25 trials is probably even a sort of overkill. So that's what that was our lesson takeaway from this tutor. So, we could do all kinds of analysis with this data that we have. So what we did was we tried to fit this to an exponential decay model in which we assumed that in this case, we actually followed the Thorndike's model in which was actually done long time ago, probably 100 years ago, wherein Thorndike was trying to see how a cat learns. There was some kind of research done by Thorndike. I don't remember it exactly, but somehow how a cat learns to get its food or something like that. So by modeling this like an exponential decay, we were able to extract some components, A, B, C. This was the modeling curve we used, A, B, C, where A represents the prior knowledge, the level of prior knowledge, B represents in arbitrary units, B represents the learning rate, and C represents the residual error. So we see that in the case of positive component, we start out with somewhat of a lesser error rate. So which means that the students had a prior knowledge, a good prior knowledge, and then their learning rate was about 0.39 arbitrary units. Whereas in the case of negative components, their prior knowledge was very less, which means that their error level was very high, but their learning rates were actually much higher in the case of negative components. So, and we saw that within about 5 to 10 tries, the students are able to get the concept really fast. And also, to test whether our tutor was really effective or not, we did this kind of a test. We did a pre-test and a post-test. So in this experiment, we used two different groups, a control group and a tutored group. So in the control group, what we did was, in the control group, there was actually no intervention, which means that we gave them a pre-test, and then the students were actually attending to a lecture, which is not related to the topic of question. And then we see that in this case, when you look at the blue graph here, there is basically no difference between the pre-test and the post-test. Whereas when you see the orange graph here, we see that in this case, the students were able to score in the pre-test, the score was low. It's about 48% before in the pre-test. And then after this, they did the tutor here, and then they did the post-test, and their scores jumped from 48% all the way to 94%. Right? So which basically tells us that the tutor is actually working. Now, this was the control group was a no intervention group, so we cannot say really whether, at least from this study, we are not able to make out whether this is more effective than other methods. But this is what we did, and this is what we have as data. And this is actually one of the other tutors that we made. This was used to teach physics students about energy and power. So in this case, the problem is actually shown to the students. An electrical appliance consumes so much electricity during its operation. Power rating is so much. So how many hours did it run, and so on. And the same thing here also, the students, when they enter the correct answer, the answers are highlighted in green, which means that the answer is correct. But if they have questions, they can actually take, if they don't know how to proceed, they can again take hints. And hopefully with the hints that are provided to the students are able to learn how to do these type of problems, right? And we used a small flowchart method to find out how to give our hints. So for example, what we did was, so we thought of how many joules of energy did the appliance consume. So what do we do if the students give the correct answer, or if they do not give the wrong answer? How should we structure our hints? So this was all, we made a small flowchart for ourselves in order to structure the hints and to decide what kind of hints to provide for the students. So that's just one example. We have also made other tutors. This is actually data structures and applications tutors that we made for teaching computer science. And then we made other tutors to explain scientific notation to students, how to express numbers in scientific notation. The same thing, scientific notation here, calculating magnetic force. And also we did this tutor wherein we tried to teach students how to apply Newton's second law. This was actually implemented with students that are not physics majors. So Newton's law and applications are totally new to them. So we have basically done quite a few tutors, and we have implemented this with our students. So I'll take some time to just do a small demo of some of our tutors at in the Tutor Shop website, if that's okay. Hello? Hello?
Yes, that's okay. Please.
Oh, okay, very good. Yeah. All right, good. All right, I'll stop sharing the screen, and then I'll go to, yeah, and then I'll share. Okay, and then I'll share this screen. Okay, share the Tutor Shop screen. Yeah, this is this Tutor Shop screen. So you can share, you can see my screen, right? Can you see my screen?
No, I'm not seeing it at the moment.
Oh, okay. Okay, screen 2. Yeah. All right. Yeah. How about now?
Yes.
Very good. Very good. All right. Okay. Okay. So assignments and vector components. So this is the tutor that I just showed. So here is the thing. So it is actually asking me for the vector component. So this one, this is a different type of monitor, so it's not showing up exactly well. But for the monitor in which we use with our student, it was actually showing up pretty okay. So anyway, so in this box below, enter the X and Y components. So in this case, the vector is 9.1 units and at an angle of 34 degrees to the X-axis. So suppose I'm a student that doesn't know how to work on this problem. I have absolutely no clue how to do this problem. I ask for a hint. So the hint tells me that the vector component is given by AX being equal to the magnitude of A times cosine of theta, right? So I now take my calculator and I try to work this out, A times cosine theta. So calculator, so that's 9.1 times cosine theta. Let's see, 9.1 times cosine theta. So anyway, let's try, let me try to enter some value here. Let us say I get a value of say 4.6. So now it highlights in red, which means that I did a mistake. So my answer is wrong, so I should try again. So I take another hint. So this hint is not enough for me. So let's see, I take the next hint. So if it says, so if the projection lies along the positive x-axis, it's positive. If it's on negative x-axis, it's negative. If I still cannot get the answer, then it tells me that the answer is 7.54 and I can enter it here. Now it highlights in green, which means that the answer is correct. Then I go to the AY and it's the same thing. Now, just for the sake of keeping this demo going, let me enter the correct value here. So now I press the done button. So that will now take me to the next problem and this goes on. So this is our tutor for the X and Y components of the vector. I would like to demonstrate one other tutor that we did in economics, please pardon me, I'm not an economist myself. This actually, I did it in collaboration with one of our economics professors. I made the tutor, I made the program for this tutor, but actually I don't know how to calculate the price elasticity. So let me make my best effort. So, okay, so this is actually a price elasticity tutor that we implemented in an economics classroom. So from the graph shown in the figure, calculate the price elasticity. Hover your mouse over the points to show the price. So for example, in this case, calculate the percentage change in quantity and enter it here. Now, the professor taught me a long time ago and now I forgot. So I don't know what to do. So let's take a hint. So this value is equal to the change in quantity divided by the midpoint of quantity. So use Q2 minus Q1 divided by half of Q1 plus Q2 to find this number. So I'm gonna do that. So Q2 minus Q1, that is 19 minus 5, that is 14 divided by the average. So this is 11 and 5. 5 plus 11 is 16. 16 divided by 2 is 8. So 14 divided by 8. So now I'm gonna enter 14 divided by 8, that is 1.75. Okay, it highlights in red, so something is wrong. Change in quantity. Okay, okay. Okay, so Q1 is equal to 5 and Q2 is equal to 19, that's right. 1.17, okay. I think I used the formula wrongly. So it's 1.17, and now it highlights in green, which means that the answer is now correct. All right, now this percentage change in price. Okay, percentage change in quantity. Okay, I made that mistake. Yeah, so that's 14 divided by 5 plus 19 by 2, which is 24 by 2, which is 12. So that's 14 divided by 12. That's what. And that is 1.17. That is correct. So now I take a hint again. So I made this. Okay, so this is P2 minus P1 divided by half of P1 plus P2. P2 minus P1. Okay, so P2, this is 11 minus 5 divided by 8. 11 minus 5 is 6 divided by 8. So 0.75. Is that correct? Oh, no, that's wrong. Okay. No, okay. Yeah. P2 minus P1 divided by, oh, okay. It is P2 minus P1. All right. P2 minus P1. Okay. P2 is 4 and okay, that is 11. Oh, okay. P1 is 4 and P2 equals 11. Okay. All right. So the answer should be 0.93. Okay. I made the mistake. 0.93. Okay. Now it highlights in green. And now we can proceed. So in this case, elasticity of demand, I have to know how to calculate the elasticity of demand. So I forgot, I don't know, and I'm gonna use the hint here, so 1.25. So as the student basically progresses through this, so this is the correct answer, and this is the, okay, so this is an elastic demand, so should we need to increase the prices or decrease the prices? Yeah, decrease, that's the correct answer, and then the student basically walks through the tutor, and then they ask for the next tutor, right? And this keeps going on and on and on. So that these are just a small demo of some of the tutors that we made in economics. So one thing that I want to point out here is, so how did we make these tutors? So we basically used the CTAT program that was provided. So we used HTML to make the HTML and CSS to make the interface, and then we use CTAT to program the behavior. We basically were able to program how exactly the students should proceed and what kind of hints we should provide and so on. So, we used a little bit of JavaScript also to sort of make sure, you know, we catch or we don't penalize students for very nominal errors. For example, you know, if the students just rounded off the numbers, we don't want to decrease points for that. So in order to catch all those things, we used a little bit of JavaScript, but it was mostly HTML and CSS. Now the good news about this, you know, JavaScript has plenty of libraries. For example, all these graphs were actually made with some of the libraries that we have in JavaScript. So which means that there was a sort of little programming that we had to do, and a lot of programming was taken care of by CTAT, which is why, you know, even though we are not computer programmers, we were able to program tutors like these and implement these in our classroom, undergraduate classroom, in such a manner that we could provide an improved student learning experience for our students. So that's all I wanted to talk about, and I'll be happy to discuss anything in particular that you may have.
So thank you, Vasu.
Thank you. Yeah.
There
yes.
doesn't appear to be any questions that have popped up. But I think you've really done a good job of outlining all of the capabilities of the CTAT tutors and talked a little bit about your development.
Thank you. Yeah.
I have some questions.
Yeah.
This going. You might have touched on this already, but how long did it take you to kind of come up to speed and learn how to do how to develop these tutors?
So in my case, it took about, to make the first tutor, that was really challenging. It took me about maybe 2.5 or 3 months. But after then, you know, we kept progressing from there, and then we were able to make tutors in about, say, 3 to 4 weeks or less. But also, you know, we don't, our effort is not full-time. So we only do part-time effort. And even with part-time effort, we were able to make the tutors within, say, about 4 weeks or so.
Were
Yeah.
you surprised by the results, or did you pretty much know going into it that the use of these tutors would help with learning?
No, we were actually surprised by some of the results. Even though overall, we had a good idea of what to expect. I mean, we intuitively felt that certainly the tutor will do a good job of improving student learning. But to be able to see these happening quantitatively, that was actually a very interesting insight. Because we saw that, when the students were working with the tutors, even with about 5 to 10 trials or so, the students were able to, get the point and understand how to make, how to understand how to calculate the X and Y components, which is actually a great thing for us. Right. Basically, we were able to get the entire class up to on the same page by way of this tutor, which is what we felt was great about the tutor.
Yeah, that's super nice. Being able to see where students are in their progress and what they're struggling with is, key to all of this, really. So you started out this process by developing some tutors, and then it sounds like you taught some others how to do it. Is that how it went?
Yes, yeah. So I have some students who work for me from time to time, so I have my students usually make the interface, and then I try to make I try to program the behavior of the tutor, how exactly the tutor should respond based on what the input the student gives and so on. So now initially we started out with physics, but now, we got a small grant from Clarion University to develop these kind of tutors for mathematics. And like I said, recently I just presented these results at the World Conference on Online Learning in Dublin, and there was a lot of interest that it generated. So this is actually the biggest thing is, now every, just like, for example, YouTube, revolutionized videography by, letting any one person, even amateurs basically do their own videos. Or just like Airbnb empowered everybody, anybody with a home to be able to let out their own homes for rent. The same way, CTAT basically, I think it empowers every teacher. Anybody who is a creative teacher, somebody who can design the tutors, has now the capability to build the tutors for their class, which is what I think is great about CTAT.
Yeah, that's fantastic.
Thank you.
So thank you so much. And know that this is recorded, so that we'll be putting this out on our YouTube channel.
Very
and
good, yes.
I know that it looks like Vincent wasn't able to join us, but Jonathan, do you have anything you want to share about the future of CTAT, or where it's headed?
I did. Can you hear me now?
Yes, yeah, I can hear you. Yes.
So we're trying to do improve the CTAT authoring tools and make them more available by turning them into a web application.
Okay.
If it's of interest here, I can show a little bit about what authoring in CTAT is like.
Yes, please. Yeah.
Yes, that would be good.
Sure.
I'll try to keep this very short.
Yeah.
But if I share my screen, CTAT, says Zoom meetings is not responding. So
yeah, I had to stop sharing before you could share, so I think I just did that.
Oh, all right. So maybe I tried too soon. And I'll wait for a minute to see if my machine recovers. It might not. The idea that Vasu was demonstrating, or the tutors that he was demonstrating, were created without programming through a technique called programming by demonstration, where instead of writing code, an author, in effect, takes the student interface, in this case, the screen where the vectors were shown, and demonstrates different solutions. Those different solutions or different behaviors by the student are recorded in what we call a graph. The graph here is a computer science term. It looks like a network or a series of boxes and arrows where each box is connected to a next box by an arrow. The arrows are links. They represent the student actions. The boxes are states in the solution as the student entered the x component of the vector, as the student entered the y component. So my machine just recovered, and I'll try to show this. Perhaps you can see a tutor that's built for adding fractions on the left side of the screen, and what looks like this this graph or this network of boxes and arrows on the right.
Yes.
So this is a simple tutor that's meant to teach fraction addition, and to just see a little bit about how the tutor works. If I set CTAT to be in test tutor mode, that is, the tools are mimicking the behavior of the student. Then I could enter a solution, which might be common denominators of 24, and then let's see, the numerator here I think would be 6. A second numerator here would be, if I get it wrong, it will tell me it's wrong. If I ask for a hint, divide each denominator and then multiply the number. So this is a good deal of what Professor Aravan just showed us. And you can complete the problem. If at this point you think you're done, it'll tell you you're not done. So if you need to ask, so it asks you to simplify your fraction, and it's what it's asking for is to get to the lowest terms. So to record all this behavior, you may have noticed that as I did the steps, they were getting highlighted down this path of this behavior graph. You see the other steps are still unhighlighted. So this is the steps through the solution that I was following. An author can record more steps. So if I return to the start state, it clears the interface, and I switch to demonstrate mode, then I could record potentially other steps. Now, 24 and for that matter 12 aren't the only common denominators. 48 should also work here. And I actually programmed this in to accept 48 and 48 here, but that's only a partial solution. So at this point, a student would need to enter 12. And you'll see on the right how the graph grows when I add a new step. And so the teacher can literally create the behaviors or record the behaviors the students are supposed to perform here on the graph. We can also, for instance, perhaps the student makes a mistake. So after entering the correct numerators, the student enters a nonsense. So I have different demonstrated values here. That's why that is. Let's start here. Perhaps the student enters a different but legal common denominator here. Well, initially that begins as a correct step, but we can change it to be incorrect. And of course it's incorrect because the denominators must match the second denominator. Match the first. That's not the greatest hint, but or the greatest buggy message. And then if I take that step again, you see the, let's see, actually this step belongs at this point in the graph. So if I go to go at the start state and come down, so 36 ought to be also a legal denominator, but 24 is no longer. And in order to see my buggy message, I would, I'm already there, so that's the reason for that. Again, 72 is a legal denominator. The 24 is not. You see the error message. The graph can be annotated with skills, and that's what's determining these skill bars here. And that lets you track at a fine-grained level what the students are doing. I think I'll stop there. There are other features that I could show, but I don't want to take up more time. So thanks for the chance to show some of this. There are features by which you can generalize the behavior of these graph elements, where you can program, for instance, formulas to make this accept any legal denominator, as opposed to just the demonstrated values of 12 or 24, together with their steps where you can require students, features by which you can require student steps to be in certain orders or to be unordered. This graph right now is unordered. That's what's shown here. Anyway, I've talked enough, and probably I should stop and let turn this back to you, Erin. Thank you.
Thanks, Jonathan. That was excellent. That was what's great about it is the ability to create very simple tutors to very complex tutors that mimic student behavior. So this is really great. I'm glad you gave that little demonstration and stopped just where you did, because there's a lot of advanced features, but this gives the real basics and how to get started. So thank you. So that's all we have for you today. Thank you thank you both for presenting, and let me show my slide set again, just to show that we do have more webinars coming up in the future. Right now, the next one will be December 11th, and at that one we'll talk about how these webinars have gone, and I'll send out a survey ahead of time to collect feedback, and it'll be more of a community conversation to find out where we want to go in the next year. So again, thank you all for joining us, and really appreciate it, and have a great rest of your day.
Thank you, Erin. Yeah.
Thank you, guys.
Yeah.
Thanks, Erin. Thanks, Professor Irvine.
Thank you, Jonathan. Thank you very much.